Yeah, is it? Yeah, that's right. So I'm very excited to be here. How many of you here know what female progeny is? Anyone? Yeah, Peter. Obviously, he's gonna know. Yes.
A woman has children, and some of the children are also female. And
exactly. Yeah. So basically, descendants or ancestors of a woman. Now, when a woman is born, a female family line starts with her, right? So if she gives birth to new offspring, it can go on for a few generations. But if she doesn't give birth, it will die with her forever. So if we can use some stochastic model to model the lifetime of a woman, we will be able to compute certain characteristics related to the individual woman as well as the whole female family coming out of her. And that's exactly what we focus on. So today, throughout my talk, I'll keep using the word female family. By that, what I mean is the entire family line or descent tree coming out of one woman. And we only focus on the birth of female children because it's a lot easier to keep track of offspring of a woman than those of a man. And fertility rates, which is an important modeling parameter, is readily available for women, unlike for men. Now, how are we going to do this? First of all, let's consider a very basic model, the linear birth and death process. And now in this diagram, and the diagrams you'll see in the next few slides, all these vertical lines, when you read from top to bottom, represents the life of a single individual. So let's start with the rightmost individual's life. There the individual will start their life at time 0, wait an exponentially distributed amount of time, and give birth according to some birth rate gamma, and that's what you see in green. So like this, births keep happening until the individual eventually dies off according to some death rate mu, which you see in red. Now, the thing is, in a linear birth and death process, all individuals have the same birth rate, same death rate. But we want more flexibility in our modeling. And that's where the Markovian Binary Tree, which is a class of branching processors, comes in. It's actually an extension of the linear birth and death process, except now we are working with n transient phases and one absorbing phase. So let's consider the general Markovian binary tree first. Don't connect it to the birth of women. So if you start with the initial of the first woman here, first individual. So that individual will start their life at time 0 according to some initial probability distribution alpha of being in this phase. And throughout their life, they can transition into different phases. And that's what you see in blue. And that's governed by this n into n matrix called D naught. While they're transitioning, they can give birth to new individuals, and you see that in green. And that's governed by this n into n square matrix called B. So how does a birth happen? So if the individual is in phase I, it will give birth to 2 new individuals. So 2 branches start, who starts their lives in phases J and K, and it dies. So if the individual doesn't give birth, it will continue life like this with phase transitions and die according to some death rate vector D. So I will define all these vectors and matrices in a minute. But before that, let's connect the MBT specifically to the birth of a woman. Now, because this model is very flexible, we do a few adjustments. So in our model, the phase will be a single year of age of a woman. So a woman is, if a woman starts their life at age 0, they have to go on in order as 1, 2, 3, up to 100 plus. So our model will have 101 phases. So let's say the population starts with 1 woman of a given age, according to some initial probability distribution alpha. She will go on transitioning in order from one age class to another, and then a birth happens. So the birth is slightly adjusted now. So when a woman gives birth, she won't die. She'll continue her life according to the same mechanism, and the new offspring who starts their life will always start their offspring at life at age 0. So that initial probability distribution will be a unit vector with 1 in the first entry and 0 in all other entries, because obviously all women have to start at age 0, and they go on. So like this, the process continues. So this time, our birth rate matrix will be a Kronecker product of E0 and D1. So D1 also I will define in a while. But what we need to remember is now a woman in phase I or age class I will have a birth rate of gamma I, and a woman in phase I or age class I will die according to a death rate of mu I. So these birth rates and death rates, we approximate it using age-specific fertility and mortality rates of a woman. But the fertility rate would be adjusted by the sex ratio at birth, because we are only interested in the birth of female children. Then we go on to define our matrices and vectors. First, we have the D0 matrix, which is a matrix where you have 1 in all superdiagonal entries. So that happens because I couldn't say this before. We make an important modeling assumption that the time a woman takes to move from one age class to the next is assumed to be exponentially distributed with a rate of 1. Then we have our D1 matrix, which is a diagonal matrix with all the fertility rates in the diagonal. And finally, the death rate vector, which is a vector of mortality rates. Now, when we looked at the literature, we saw that previously there has been a study done where you use a Markovian binary tree to model the lifetime of a woman using a time homogeneous environment. So there they assume that the rates of the year 2010 remains fixed forever. And they go on to compute a number of characteristics related to an individual woman, as well as the whole female family, like life expectancy of a woman, mean progenies, total progenies, extinction probabilities. So inspired by this, what we did was we obtained the age-specific fertility and mortality rates of a woman, not just for 1 year, but for an entire time period from 1950 to 2023. So this is available publicly to anyone on this United Nations database called the World Population Prospects, and it's updated regularly. And it's available at a very granular level. It's also in the time series format. So here you see a snippet of the data we have obtained. We see the age-specific fertility and mortality rates for all these years that I said before for a 30-year-old woman for some countries. And we see that obviously the rates don't remain fixed forever. They have changed over time, right? So just like for a 30-year-old woman, you will see this for all other age classes as well. So what's our new contribution going to be? Instead of modeling the life of a woman using a time homogeneous MBT, we are going to consider these changing rates and model it using a time inhomogeneous MBT. So every year the rates change. So within one time interval, the time interval would be time homogeneous. But when we glue all these time homogeneous intervals together, we get a time inhomogeneous Markovian binary tree. So now we need to use matrix-analytic methods to compute those same same characteristics that I showed you before. So we need to find new ways to do that. So just to tell you now, the model definitions will remain the same. The only difference is say the process starts at time 0, rates change at year 1, 2, and so on, right? So what happens is our main matrices and vectors will also change. So earlier we had D0, D1D. Now we have D0K, D1K, and DK. And this K superscript represents the year to which these rates belong. So far, do I have any questions about the model before I go into an application? Yeah. Yeah. So we do that actually because we need to keep the model stochastic, first thing, because it has the Markov property, and it makes the model more tractable because we already have so many phases, right? We know, okay, that the woman ages every year, true, but we need to make the model stochastic. So we do that exponential assumption. Because see, yeah, it's more like it's a embedded Galton-Watson process. So rates change discretely, right? Rates change discretely. So within that year, it's a set of rates that we have. So I mean, not really, because see, when we do the computations, we consider embedded Galton-Watson process for some characteristics, while for the rest we don't. But I can answer that. We can have the discussion maybe after we're done. That's interesting, yeah. So we have collected the data of about 20 countries so far, but today I have selected about 8 countries to do some interesting comparisons and contrasts. So we start by defining the probability generating function. In equation 1, you see the conditional PGF of the population size at time t, given that the MBT started with 1 woman in phase I at time 0. So those are the individual entries of the vector. Then we get FTS as our final vector. Now the thing is, our rates change every year, right? So each time interval will have a unique PGF vector. But if we want to get the PGF of the overall population at some time period in the future, using properties of PGFs, we can show that it's going to be the composition of all the PGF vectors leading up to time t. And that's what you see in equation 2. And we define this here because you will see that for all the computations we do as we go on, this becomes the foundation. So today we will be focusing on two characteristics. First up, we have mean family size. So by mean family size, what I mean is the mean number of female descendants alive at a given time in a family line that started with a single woman in phase or age class I at time 0. We will also look at the variability of the average number of descendants. Then we will move on to extinction. So we will be looking at a criterion to identify if a particular family line has a positive chance of survival or not. And we will also approximate some extinction probabilities. So mean family size. Now to obtain a formula for the mean family size in the time inhomogeneous case, we use the existing formula for the time homogeneous case. And this mean population size matrix is computed in the time homogeneous case using MT, which is an exponent of another matrix called omega t. Omega has some Kronecker sums and products involved. So just to give you an understanding, one entry of this mean family matrix here is the mean number of women in age class J alive at time t generated by a woman in age class I. So like I said before, since the rates change every year, every interval will also have a unique mean population size matrix. So that's what I have defined by equation 4, and these become inputs for our proof in the next slide. So what we do is we take our PGF, differentiate it by S once and substitute S equals 1. And this computation is quite easy actually. We will see that if you want to get the mean population size matrix at time t, that we will arrive at this cumulative product of all the mean population size matrices. Next, we move on to the variance of the family size. Now, to get the variance of the family size, we need to first define the second factorial moment matrix. Again, this slide, just don't worry too much about the maths. This I have just defined the existing second factorial moment matrices for the time homogeneous case. Star basically represents the second factorial moment matrix. We do some numerical computations here. But in the time inhomogeneous case, what we do is we differentiate the PGF twice with respect to S and substitute S equals 1. So this proof is a bit complicated. I haven't put that into this, but we can recursively show because it involves, matrix derivatives with respect to chain rule and the product rule. So it's very complicated. So recursively, we end up with equation 9. And using the second factorial moment matrix and the mean family matrix, we obtain the standard deviation vector, where one entry is the standard deviation of the total family size at time t, conditional on the age of the first woman. That's what you see as sigma t. So that has a lot of, now we spoke about a few matrix differentiation techniques, but I think the interesting part is what the results look like when you apply these formulas to the real world data. So here what you see is the average number of descendants alive at a given time, given that the family started in the year 1950 with one newborn woman. And we have data for about 8 countries here. And what we see is the rate at which the family lines for women in Afghanistan, Congo and Niger grows is much higher in comparison to the other countries. Like for example, you can see by the year 2024, on average in these countries, you have about 6 to 7 women, female descendants alive. Then there's a huge drop to the blue line. And I mean, at the bottom, you can see South Korea, where on average, even after 75 years of the family line starting, you only have about 2 to 3 descendants alive. So the interesting thing is you can actually connect what's going on in these countries to these results here. For example, the literacy rates of the women in these countries are very different. The access to contraceptives, birth control is very different. Economy is very different. So it's interesting to see that you can actually connect what's going on to what you see here. Next, we have a different matrix, which gives us a bit more of information. So here you see the coefficient of variation of the family size that I showed earlier. And in general, we see that as with time, the variability increases for the average number of descendants alive. But what we can see, an interesting feature in this graph is, based on this characteristic, we can divide these countries into one of the three baskets as like high, mid, and low. For example, in the lowest bucket, we have Australia, Canada, and US, and we see that the coefficient of variation is less than 1. This might be due to the fact that, yes, they have low fertility, but they also have low mortality. And these are countries with better access to healthcare, they're more developed, and there might be the fact that, the way their population grows, the female family grows, is more predictable, it's more matured. On the other hand, if you look at Niger and Afghanistan on top, their CV values are very high. Again, they have very high fertility rates, but at the same time, they have very high mortality rates. So that might be incorporating a certain level of variability into the family sizes. Then another interesting thing we see here is that previously we saw that Congo had a pattern similar to Niger and Afghanistan. But in this graph, it has a pattern similar to South Korea and China, although they're very different countries. I mean, what's happening in those countries is very different, right? So this might be telling us that these are just, we're just trying to get some insights that Congo does have high fertility and mortality, but it might be having better survival patterns in comparison to Niger and Afghanistan. So here I need to show you, for China, you can see that the line sort of becomes flat in the years 1960 to 1980. And during that time, the one-child policy was introduced to China. Maybe it has an impact on what we see here right now. Next, we move on to extinction. But before moving on to extinction, I defined the probability vector Q, where Qi is the conditional probability that a female family generated by a single woman becomes extinct, given that she was in phase I at time 0. Now, for an irreducible multi-type branching process, there's a very well-defined theorem to categorize a branching process into one of these three categories. So it's based on the Perron-Frobenius eigenvalue rho of omega. It says if rho is less than 0, every entry of Q will be equals to 1. That's a subcritical processes. Then if rho is equal to 0, every entry of Q would be equals to 1, and that's a critical process. And if rho is greater than 0, every entry of Q would be strictly less than 1, and that's a supercritical process. Now, when we go on to the time inhomogeneous case, the theorem that's available just divides a population into two classes. Okay, so that is actually based on an infinite series of terms, and these terms are actually the Perron-Frobenius eigenvalues of the kth mean population size matrices that I defined before. In short, what this theorem says is, if the infinite series diverges, the population goes extinct with probability 1. And if the infinite series converges, the population has a positive chance of survival. So what we want to do is, we use this theorem to get an understanding if a particular family line has a positive chance of survival or not. I know we only have 75 years of data, but that being said, we will never have fertility or mortality rates until infinity. So we are going to get an indication about what's going to happen to these family lines based on a portion of an infinite series. So before applying this theorem, we do a few adjustments to our model to satisfy some conditions. First of all, we truncate the model at age 49 of a woman, because that's the last fertile age of a woman in our model, and this makes the matrix irreducible. And we also show that as time goes to infinity, the forward product of these matrices becomes weakly ergodic. So as a first step, what we did was, for the same countries I showed before, we plotted the partial sums of the mathematical series with time. And we see that except for Afghanistan, Congo, and Niger, all other country lines looks like they're diverging. But obviously, this is not good enough for us to make a conclusion. It's not concrete enough, right? So we use the direct comparison test of a mathematical series here. So the idea is to find some bounding series with terms BT. And based on the convergence or divergence direction of the bounding series, we're going to say something about the convergence or divergence of the series related to that country. And you can't use this method for all countries, obviously, but we were able to do it for the countries that we're discussing today. And for most countries, the geometric or the power law series became the bounding series. So let's just have a look at the results. Now here in the dashed lines, you see the countries that gave us an indication that their family lines are going to go extinct with a probability of 1, whereas the solid lines, which belongs to Niger, Afghanistan, and Congo, were the only 3 countries that showed that they had family lines with a positive chance of survival. Now here I need to reiterate that we are not talking about the extinction or the survival of the female populations of these countries, but about the family lines generated by one woman of that given nationality. Next, we were also interested in the distribution of time until extinction. So here I define the random variable TE, where that is the time until the family line or the MBT generated by a woman in a given age class becomes extinct. We can get the conditional distribution of TE by substituting S equals 0 in our PGF. Now, here we assume that the rates of the year 2023 remains fixed forever. And why we do that is, so here you basically see the distribution of time until extinction for a family that is generated by one newborn woman in 1950. And we only have rates for about 75 years. But we want to see the distribution at least in the next 100 to 150 years. So what we could do is assume it's constant after the year 2023 unless we do some forecasting. And that's why that area is grayed out. So we believe that the main factor affecting this graph is the degree of infant mortality of a country. Now, if you look at US, Canada, and Australia, the bottom 3 lines, we see that as soon as the family line starts, the probability of going extinct is almost not 0, but it's very low. And that contradicts my previous indication. But what is actually happening here is these countries have very low infant mortality because they have better healthcare. Women are have more access to better facilities. So the chance that the first woman in the family survives is very high. So she will live for she'll obviously survive until she comes to old age. Then the next challenge is after about 50 to 60 years, we see that the probability starts going towards 1. And that might be because these countries also have the chance that those women might never have kids, or also their childbearing age is quite late. Then on the other hand, if you look at the topmost lines, which belongs to Niger and Afghanistan, we see that as soon as the family lines start, in fact, for all the other countries, the probability of it going extinct shoots up. And that's because in these countries, they have high degrees of infant mortality. For example, for South Korea, it was just after the Korean War, given that it started in 1950. And in these countries, the real challenge is if the first woman would survive or not. If she survives and gives birth, then for the top 3 countries, we see that it's just about, it's just like the family line is going to sort of explode. And that's why it never reaches 1. Now, the interesting thing is, say that I change the year the first woman was born in from 1950 to 1990, okay? Then we see that the lines of South Korea and China become very different. They actually show a very similar pattern to Australia, Canada, and US from the beginning itself. And why not, right? Because China and South Korea, by the time it was 1990, had become very different countries. They had become a lot more developed. So this is quite interesting to see that with time and the year the first woman is born in will have like a huge impact on what's going to happen. On the other hand, if you look at Niger, Afghanistan, and Congo, the values have changed slightly, but the pattern remains pretty much the same. Finally, we are going to approximate extinction probability. So I defined what Q was earlier, but Q actually is the limit of GT, sorry, in the interest of time, I think I'm going to just rush this slide. Here we have the extinction probability vector. How we approximate it is by substituting this Q value that we have computed using the methods for the time homogeneous Markovian binary tree into our equation 12. Again, we are assuming rates of 2023 remains fixed forever. I'm happy to speak more about this after my talk, but I'll just show all the results. So here what you see is the extinction probabilities of families generated by a woman in 1950 as a function of her age. And we see that for all the countries that I have listed there, it has a U-shaped curve. So the lowest probability of extinction is when the family starts by women in the age group 15 to 25. But what's interesting here is, or quite rather concerning, is the curve of South Sudan. We see that for all age groups, the family line started by all women is a lot higher in comparison to the other countries. So this is telling us a lot about the level of mortality in these countries, right? So with that, I come to an end of what I've been talking about today. So we were able to show that the time in homogeneous MBT is suitable to model the lifetime of a woman. And we also saw that so many countries have very different ways of their family lines progressing due to various factors. We also saw that some countries will have the same pattern, but they have completely different things going on in their country. And we believe that the results that we showed today would actually help governments and various other institutions for policy making and resource planning in various ways. There are so many stakeholders who might be interested in this. As we go on, we would be computing other characteristics that I showed before, and we're also interested in forecasting age-specific fertility and mortality rates because that has a big impact on our modeling. Finally, I would like to thank the University of Melbourne and the Fields Institute for funding my talk today and giving me the chance to come here and present to all of you. Sorry, I've gone a lot more than I was supposed to, but thank you very much, and I'm happy to answer any questions.